Hi everyone, today we'll do a review on the topic of regression, simple regression model, SRM, and we want to learn how to use, we're reviewing steps that we need to use on JMP to get some results. So I remind you that before we start any kind of analysis, we can always start with the distribution and check distribution of our data. Let's say the question you're dealing with has only two variables, maybe percent body fat, and we want to see if there's association between percent body fat and weight, and we want to consider the regression analysis as well. So we'll check these two variables, and I have the histogram here and weight, histogram of percent body fat and weight, where I can the histogram options and make sure they are. This seems to be percent body fat seems to be quite normal, and weight is also close to normal. We just have two outliers. So remember that do not remove any outliers unless the question asked you. But if for your own research, if you want to remove outliers, this chart is actually a good chart to check outliers here. There's one outlier here, the two outliers here. The only part that will ask you to remove outliers could be on chapter 22. So the question will ask you to remove outliers and check results again and compare your results from the earlier analysis. And we'll get there almost at the end of this topic. So other things I can check: average of the two variables, standard deviations. And I remind you that if there is, for example, skewness, kurtosis is asked, you click on the red triangle. The summary statistics, click on customize, and you can actually add variance, skewness, kurtosis, and minimum, maximum, autocorrelation, trimmed mean, median, mode. You can add all of those information. You can change the confidence level from 95% to whatever value you want, right? And those values appear. You can do the same for this one. So initially, that's what I would do, just to make sure I understand what type of variables I have. I can see some graphs here. And the next step, I want to look at some scatter plots now. And for a scatter plot, you go to Analyze. One thing that I need to make sure you understand is that there is not one way to get results in JMP and in many other softwares. You can always use different ways to get results. So this is one way I'm showing you. And can we do this in different ways? The answer is yes. There are many other ways to get similar results. So click on Fit Y by X. Fit Y by X tool in JMP actually creates any analysis for any one-on-one, any association between an explanatory and a response variable, no matter they're categorical or continuous. But you know that for regression model and for correlation analysis, we need to use numerical variables. So far, what you have there. So a response variable, we're trying to control percent body fat. So we want to consider it as a response variable, and weight, we want it to be considered as X factor or explanatory variable. So far, that's all you need to do. And this is going to be bivariate on the top left. And click OK. When you click OK, you can see a scatter plot here. And the first thing you analyze, and the first type of question you would see is this a linear relationship? So far we can say yes. If the shape of this scatter did not look the way that you can 100% say, yes, it's linear relation, then what would you do? We can add some information. And one of the values that actually can tell us about the linearity of the relation is correlation R. So I click on summary statistics. And of course, moderate or strong or very strong correlations normally represent some type of linearity. And also you can look at the significant values less than 0.05 that actually make us sure that there is a significantly linear relation here, okay? Again, by just seeing a visual test, you can actually get to say, is this a linear relation or not? If it was like a circle and points were spread all over the area, or a rectangle, then it's not going to be a linear relationship. The next thing that we look at, so remember, correlation is here, significant level of correlation is here, and in this way we can say there is a significant relationship between the two variables, and confidence interval of the correlation is right there. You can find the covariance and mean and standard deviation of weight and percent body fat here. So next step is to find a fit line. Finding a regression line going through those points. So click on fit line, and it's not perfectly fitted here. We expected to see it going that way, and that could be because of few of those outliers. You can see there's one outlier here, quite far, not in the same direction as the general direction of this scatter plot. Or again, I can say that we're not expecting to remove any outliers at this point, unless you're instructed to do and see the results. So what do we look for here? We look for the line fit, the linear fit, the line equation, and line equation has a response, estimated response variable, percent body fat. You have an intercept, you also have the slope, and you have the explanatory variable. What's expected is that you understand what the intercept is and what it means, what the slope is, and what it means. So slope, in this case, if there's no weight, effect of weight is ignored in this case, percent body fat would be -12, right? And percent body fat with a negative number actually does not make sense. So there is no interpretation for it. If it was like profit, then we would say the negative sign is a loss, positive is gain. But in this case, so we don't expect to have any negative value. And one main reason is that we expect weight of people to be at a certain point and higher than a certain value. So after that certain point of value, of course, we will never have a negative percent body fat for any actual person. So other than getting to know the intercept and slope, we also want to find the confidence interval around these two values, right? So we will talk about that. And why do we need to find the confidence interval for intercept and slope? Because these are actually estimation of intercept and estimation. These both are estimation, and weight will be given for a specific value of weight. We use intercept, estimation of intercept, and estimation of slope to estimate the percent body fat. So now we did talk about the interpretation of intercept. Let's talk about interpretation of the slope. So a slope, one easy way to explain or interpret the slope is to say, if you change your explanatory variable by 1 unit, how much change do you expect to have in your response variable? Of course, as much as slope, or in this case is 0.174. So depends on the type of variable. You can also change 1 unit change to 100 units, or 10 units change, or 1,000 units change. As much as it actually makes sense, you can actually change it. So slope is very important, and the interpretation is the amount of change in response when there is a unit or 10 units or 100 units change in explanatory variable. The next number that you normally report or you will be questioned is the R-square value for regression results, and that's 0.375051. So this number, when you interpret it, what it actually means, you report it in percent. So that would be 37.5% of the variation in response. Your variation is response, the portion of variation in response being explained by the variation in explanatory variable, right? So this is very important to remember, that this is reported in percent and explains a portion or percentage of response variable, or the DV, and the variation in DV being explained by the variation in IV. The next number that you will be reporting or you will be asked is standard error, or standard deviation of errors, or standard deviation of residuals. So standard deviation of errors in JMP is actually explained under summary of fit and under root mean square error. That's the other name of standard error, RMSE, or standard error. That's 6.6. And how do we explain it? What is root mean square error, or what is standard error? Standard error is standard deviation of the errors. And what are errors? Going back to scatter plot and the fit line, the distance, the vertical distance of each point or each data value, each row of values that you have. Each person on this scatter plot, how far are they from this regression line? That difference is your error of this line, error of calculating using this line, right? So as a result, we can actually see here that the standard deviation of all these errors, error 1, error 2, error 3, error 4, and so forth. And if they are on the top of the line, they're positive. If below the line, they're considered negative. So you calculate the average and standard deviation of all of these residuals, and the standard deviation of them would be root mean square error, right? Where do we save? How do we save how do we find these residuals? If you want to know that vertical distance from the line, you can actually click on the red triangle and check save residuals. And you will see at the end of your data set, you can find those residuals. So if I click, actually my residuals appeared here. Right there. Okay, so those negative numbers, for example, the first one, the first row is actually negative 16. So let's see. First row is negative 16. That means this point is 16 units below the line. The line is considered the average estimation of percent body fat explained by weight. And our first person in our data set with a weight of 363.15 pounds with a percent body fat of 35.2 is actually way below that line. And actually the error of that line for this person is considered negative 16.07. And other numbers, if they are negative, they are below the line. If they're positive, they are top of the line. Okay. If a certain point you want to know where it is, this one is very close to the line. number 83. So I can scroll down to number 83 and find it. And that's that distance, the small distance is 0.7, right? So that's not difficult. That's quite good to know. And what else do we need? So you learned the standard error, which is RMSE, and observation, number of cases that we calculated this information based on, 252. And I told you that intercept and slope, they are estimations to help us estimate the response variable. So anytime you have estimation, you can have confidence interval or upper and lower bounds, right? So confidence interval, 95% confidence interval around -12 and 17, they can be reached or can be found here in parameter estimates. And directly you can't see them, but you can see the intercept here. You can't see the slope here, the same numbers that are up there. But to find the 95% confidence, you right click, go to columns, and you want to add some more information, right? Right click on primary estimates, lower 95, one more time, and then upper 95. So you can see that -12 is between -17 and -6. It's actually in the middle of these two values. 0.17 is in the middle of 0.14 and 0.2. So these are the lower and upper confidence level. But to calculate the confidence level, we actually need another value, and that value is a t-stat. Do you remember that we said 2 times standard deviation of your observations of your standard deviation, 2 times of your standard deviation covers 95%, right, of the observations. So we can actually say in this case that t times the standard error, the t-stat multiplied by the standard error around intercept, and t multiplied by standard error around weight, estimation of weight, cover 95%. So this t is actually somewhere around 2, and it's being multiplied by the standard error of intercept and standard error of weight. Okay, so we can actually calculate it. The calculation is not shown here. I can check that. Going to show properties. Let's see if we have any information here on that. We don't have that here, but I had a few students, they had a few problems with the software and they couldn't see more decimals here. If you couldn't see more decimals here, you right click, you click on show properties. That will give you the full value of any value you're clicking on. So what I can do here is, all right, so let's go over topic and see how these numbers are calculated. I'll really quick show you in the slides. So here is the estimation of intercept and slope. And then we have this formula to calculate the confidence interval around intercept and confidence interval around intercept and confidence interval around slope. So that's the T I talked about. That's actually normally gets somewhere around 2 times the standard deviation or standard error, right, is going to cover 95%. And the calculation is also quite simple to calculate. So you can see that you will look into the T distribution, T table, and you will find 2.014 multiplied the standard error and add or subtract to your slope or the intercept. So there's another T as well. There are two T distribution or T test being considered in simple regression model. One is what you learn here in calculation of confidence interval for slope and intercept. And the other one is this T. This T is for hypothesis testing of beta 1 and beta 0. And what is beta 1, beta 0? Beta 0, beta 0 is actually your intercept, right? If your intercept or your slope, they are 0, then you don't have any regression line. So the regression line actually doesn't work, or it's not reliable. We can't actually use it for decision making. So as a result, we create a hypothesis for both intercept and slope. So, and the hypothesis is HO is beta 0, which is your intercept, to be 0. Now you can calculate based on T distribution. You can calculate T, and based on the T value, you can find the P value associated to it. And if P value is less than 0.05, you can reject HO, which means you can reject this, which actually means beta 0 or intercept is non-zero. And we want beta 0 to be non-zero, because if it's 0, then we don't have a formula, right? The same goes for intercept. Hypothesis is that, null hypothesis is that beta 1 is 0. We hope to get a p-value less than 0.05. So we calculate T, and this is the formula for T. So this T is different from this T. Okay, this T is for confidence interval of intercept and slope. This T is for hypothesis testing for intercept and slope. So let's really quick, let me show you this T for hypothesis testing on JMP. So this is primary estimate results. This is the T I just showed you, T ratio. So it's not supposed to be always equal to 2. It's actually, it can be any number. And if it's 2 or more, that means you have a significant value. The value of your beta 1 and beta 0 is significantly non-zero. So looking at them, negative 4.67 and 12.25, right there. So how is it calculated? The B1 itself, the slope, divided by a standard error of slope, and intercept divided by a standard error of intercept, right? That's right here. But the T value for upper and lower 95% is not here. It's supposed to be somewhere around 2, and it's normally falling around 2, 1.90 something or 2.0 something. But I'm going to show you how to find it actually. So I hope you understand the difference between these two T, because it's going to be, this T is going to be a question on exams and homeworks. And normally students look for this T distribution from lower and upper 95, and they actually don't get the results that they want. So the p-value associated to the T for hypothesis test, this is the T for hypothesis, associated p-value to it is actually right here. And if it's below 0.05, we reject HO. So you don't need to calculate the T. This T, you don't need to calculate it. It's right here. And the p-value that we make decision based on is actually here. Is it less than 0.05? If yes, you reject HO. That means these two values are significantly non-zero. They are not equal to 0. Or they're significantly values that we can use them for decision making. Okay, so let me actually go and show you where to get the T stat for the lower and upper 95. All right, so this is my Excel file, and I just want to show you how to calculate this T for the confidence interval of slope, and also for the intercept case. I have 47 cases. So I type here N is 47, and in this case, we also need, for t distribution, we also need confidence level, 95%. So CI, confidence interval of 95%. And you know that confidence interval has two tails. So the 5%, so alpha is going to be, alpha is a 5%. But alpha half, right, is going to be 2.5%. Because we're dividing it by 2. One tail on the right, one tail on the left, that's 2.5%. And 2.5%, we can also show it in decimal, 0.025. And our actual confidence that we want to calculate for this t stat here is going to be 1 minus, equals to 1 minus 0.025. And again, 99% of times you won't need to calculate the t. You just can find the 95% confidence interval from JMP. And I actually showed you that here. The confidence interval after calculation is right here. But sometimes the students ask me, can you show us where that t can be found? So it's not here. So we have to actually do it manually here. Okay. So the actual confidence that I have to look for on t stat is here. And to find the t stat, I go to here and then t stat of 95%. And so degree of freedom, right? The degree of freedom is going to be n minus 2. It's 47 minus 2. And 47 minus 2, which is degree of freedom, df. All right, that would be equal to. So just type t, and then t inverse of probability is this number, 0.975. And degree of freedom is, we just calculated that here, is 45. So this one is t of 0.025. The reason is 0.025 is because we have 95%. 1 minus 95% is 5%. And because we have two tails, it's divided by 2. That's 2.5%. And n minus 2, which is right here, 0.975. Press enter, that will give you 2.0141, which is here, 2.014, right? That's rounded. So we found the t stat for confidence interval. We multiplied by standard errors of intercept and slope, and add and subtract from intercept and slope. That give you that confidence interval. So JMP made our work actually very easy. And you can see that by a right click on primary estimate, going to column, you can check this to lower and upper 95, and they appear right there. All right, so this is the difference between the two t. The other t for hypothesis is here. So it's very important you don't make mistake on these two different t's, because that can be confusing on exams. All right, so far we did talk about the regression line, intercept, slope, confidence interval of intercept and slope, the t-ratio, p-value that we determine if we should reject HO or not. So t, if it's t more, the absolute value of t is more than 2 or 2, we can reject HO. Equivalent to that is p-value to be less than 0.05, and equivalent to both of these is if 0 is not included in the intervals. they're both negative or they're both positive. That means 0 is not in the middle. As a result, we can say we can reject HO. These are different ways you can reject HO. So what is next? The next step, I hope you remember, that there are conditions that we need to check. We already checked the condition of linearity of our scatter plot. The next step is to check residuals. So are residuals normal? Are residuals having similar variances, or are they homoscedastic? And also, are residuals independent? These are 3 other questions we learned earlier. So to check those, we go to the linear fit, red triangle, and check plot residuals. So linear fit, click on red triangle, and click on plot residuals. And this is not the only way to get those results. This is one of the ways. Okay, there are many other ways to do this, and this is how I do it. So click plot residuals. So these are the residuals and how far they're from the line. That's the regression line, and how far they are from the line is actually represented here. How many of them are in this range? How many of them are this far? And that creates actually quite perfect normal distribution here for us. And we also, we don't use this for normality. We actually use this for normality. Residual normal quantile plot or QQ plot. And what we expect to see here, we expect to see a set of the points where they're all on that line. And if they're not all on the line, and if they're still between the upper and lower bound, that's still okay. If all of these points fall, at least 95% of them fall between the upper and lower bound, this indicates that we have normality of residual. So normal quantile plot is going to tell us if data are normally distributed or not for the pattern and for having homoscedastic residuals. So for homoscedastic, from left to right, we want to see, do we have changing variations? Is the variation changing too much? Is on one side, is it they're very close and the other side very far? The answer is, in this case, the answer is no. By ignoring just a few outliers, just ignore a few outliers, the rest of them are actually quite having the same variation. So variation vertically checking from left to right, you can see that it's not changing that much. So we don't have any problem with the changing variations, and we actually have a homoscedastic residuals here. Homoscedastic, also normal, and the next one is the independent. One way to recognizing independence of residuals is just checking the residual by X. And here I don't see any pattern. I don't see it going up or going down. That's one sign. The other way to check that, and on chapter 22, we discussed that topic, analyze, fit model for, and Devon-Watson test is for independence of residuals. Residuals are supposed to be independent, normal, and homoscedastic, right? So we already checked normality, we checked homoscedasticity, and now we want to check the Watson test for independence. So we put this here, put weight down here, minimal report, because we don't want to see all the results. We just want to see the results that we need. So percent body fat goes to Y, and weight goes to construct model effect. You have more options here to add some diagnostics, and we want row diagnostics. Go to red triangle of response, row diagnostics, and find the Durbin-Watson test. And the Durbin-Watson test can tell us if residuals are independent or they're not independent. So click on residual Durbin-Watson test, and that would give us at the end of, after the primary estimates, at the end of results, you have Durbin-Watson of 2.2 with a p-value of more than 0.05. All right, so I need to explain what autocorrelation means here, just really quick for those who forgot. So the hypothesis test for the Durbin-Watson is actually HO is rho, which represents correlation, is equal to 0. Rho equal to 0, in fact, means there is no correlation, right? Correlation. And that actually means residuals are independent. And that's what we want. We want residuals to be independent. So we don't want the Durbin-Watson test to reject this. If we don't want this to be rejected, that means p-value has to be more than 0.05. In this case, we could not reject the hypothesis that rho is 0. And rho is 0 means residuals are independent. So we could not reject it. So we don't have a proof that residuals are correlated or are dependent, which is not good. Residuals are supposed to be independent. Don't forget it. All right, then we have explaining the autocorrelation. So let's say we have errors or residuals. So correlation among residuals, we just have one column of residuals. There is no X and Y so that we can find the correlation or association here. As a result, we create lags, lag 1, lag 1, lag 2, lag 3, and how lags work, you just copy the same data and paste them one row lower. And this way you can find the correlation between the two similar data sets, right? Or same data set in two different lags. So this is actually called autocorrelation, means correlation of residuals to themselves, because they're the same data in different rows. And this way we can see if there's a correlation here. And if there is correlation, then they become dependent. And it's not good for regression. We don't want patterns, right? We don't want a pattern on residuals. And in this case, you can see that Durbin-Watson test actually tests autocorrelation, checks if there is a correlation between residuals themselves, like this. And the p-value, if p-value is less than 0.05, then there is a correlation. It's not less than 0.05, so there's no correlation here. Okay, so there's no autocorrelation, and as a result, we can say that residuals are independent. All right, the next or the last topic to be covered is the prediction intervals or the prediction formula. The prediction formula is right here. That's your prediction formula. So we don't need these results anymore. And the prediction formula is this formula. So you estimate percent body fat using that formula. So what is actually important for us in prediction formula is that we want to use it by giving a certain weight. We want to estimate the percent body fat for that person. So the calculation we did here was actually based on some averages made on our data set, based on these rows, right? But now let's say we have a new information and we want to know, without actually knowing the percent body fat of that person, we want to know if we reduce or increase to a certain point, what would be the estimation of percent body fat, right? So by plugging in a value for weight, let's say 200. If I give 200 to weight, I can calculate the percent body fat. But that's an estimation. And since it's an estimation, I can actually have a 95% upper and lower limit, right? Around that value or like a error of margins. or margin of errors. So for that, what should I do? For that, I go to my linear figure red triangle, and first of all, I can calculate all the predicted values by clicking on Save Predicted. That will create the formula for me, and any value I add, it actually can calculate it for me. So I click Save Predicted, and you can see that at the end of your data set, that's the predicted value based on the formula. And if you see, the actual value of percent body fat of that person with a weight of 336 pounds, the actual percent body fat we calculated using lab results was 35.2. We used the regression line to calculate it, is a 51. How far is it? As much as the residuals. That's a 16 point below the line. So that's the line. It's the y-axis of the line. That's the estimation of percent body fat. The percent body fat we have in this row is 35. That's actually the actual percent body fat, and the difference is the error right here. So let's look at if the question gives you a new value. If the question gives you a new value, how do we find the predicted value here? So we go down here in a new row far to the left, because predicted formula is actually created. So if I give a value to weight down here on an empty row, let's say you tell me, you ask me, if a person has a 200 pounds of weight, what's their percent body fat based on the regression line? How do we predict it? 200 on weight right here. And if I press enter, none of these are going to give you any numbers, but the predicted equation actually give you some results. Click and go to the right and look, 22.8. A person with the 200 pounds of weight, we could estimate that they should have, in average, they should have 22.8% body fat. Okay, so now the question is, this is estimation. How about the lower and upper 95% around it? To do that, go to your regression results, which is this one. Click on the fit line rectangle and click on individual confidence limit formula. It's going to create upper and lower bound around. It's going to add the results to the right-hand side of your data set. Click and go far right-hand side. That's the results. So for a person with a 200 weight, we predict percent body fat of 22.8 with the lower 95% of 9.7 and upper 95% of 35.92 of the predicted value. It's two columns. So any time a new value is given and lower and upper confidence are required, it actually can be calculated as easy as I just showed you. So use that for if you had such question. Okay, so one more thing that students normally ask me is how to add a new variable or how to manipulate this data and create some new variables. To create a new variable, you can, in fact, click on column, new column. If you click on this, a new column will be created, or there's one more way you can do that, and that is, let's say, I select this and I want insert a column. I can insert a column. Another way is at the end of your data set, you have a new data table here. It is empty. right click and click on new column, or double click on the top. It will create a new column. But I've already created a new column here, so I'm going to use it to make some calculations and show you. So let's say I need percent body fat to be copied here. I right click, click on formula, and if I double click on percent body fat and click apply, click OK. This column is the same numbers as a percent body fat, and I can just change its name to percent body fat, maybe underline 2, because I want to do some calculations on it, right? Then if you need to have more calculations, let's say you want to have your predicted formula to be here, or you want change weight based on pounds to kilograms, and the formula is given to you, and put it here. So you right click and change its name to weight in kilograms, for example, and then use the formula in the formula chat, right? Formula page. So you go here and click on formula, and all you need is to delete this, and weight multiplied by whatever number is given to you. You press enter, it's going to convert it to kilograms. Or maybe you want to just create your predicted formula. So predicted, and click OK. So predicted, actually percent body fat, predicted percent body fat. And I want to create it using formula. So I know the results of my regression. I open it and I look at it. It should be right here. Where is it? Not this one. Okay. It's this one, right? I want to put it here. So I don't want percent body fat. I want to delete this. I copy this number. Copy and paste. And then there's a plus. I click plus. And then 0.17. Right click, copy, paste really quick. And then I want multiply. So I have a click here, multiplication. And here I have weight. I don't type weight. I just find weight and double click on it and click apply and click OK. Right? So this is the predicted values. These are the predicted values. For the first one, do you remember it was 51 versus the weight of percent body fat of 35, which the difference was 16. So that's actually the predicted formula we found. JMP actually gave us predicted values earlier, right here. Predicted. This is the same. This is using the same formula I just actually used to create this, right? So you can use formulas to actually manipulate data and create new columns and add 2 columns or do a lot of other things. So I hope today's session was actually good for you and you could learn some new stuff for working on simple regression model using JMP.